Hi again, everyone. Welcome back to our Calculus 3 class notes. We're on the last page of section 15.4 where we're talking about using the polar coordinate system to evaluate double integrals. So using polar integration, find the area of the region R in the xy plane enclosed by the circle x squared plus y squared equals 4 above the line y equals 1 and below the line y equals square root of 3x. Okay, so this is the shaded area here is that region, right? So here's the circle, x squared plus y squared equals 4, radius of 2. Okay, and then the line y equals 1 is this horizontal line across here. So we want to know we're 1 above that, but then below the line y equals square root of 3x. So y equals square root of 3x is this line. Okay, so we have this region right here. Now, let's consider setting up as a rectangular integration first. So if I set it up as dx dy, I can say that y goes from 1 to the square root of 3, right? Y goes from 1 to the square root of 3. As y is going from 1 to the square root of 3, it's going from this lower function of y. So x equals, solving this for y, 1 over the square root of 3y, to solving this, the equation of the circle for x, I get x equals square root of 4 minus y squared, and that'd be the upper half of the circle, even in terms of y, right? Because if I'm standing on the y-axis, that's up in the positive part. So x equals the positive square root of 4 minus y squared. So that's the limits of integration for the x integration. So putting this together, if I were to go ahead and integrate the first one with respect to x, I get x. Evaluate that from x equals 1 over square root of 3y to x equals square root of 4 minus y squared. I now need see something where I would need to use trig substitution. And I will do an example for you later of doing trig substitution because I know you need to remember how to do that. But I'm going to stop that for now, saying because I would need trig substitution and show you how much easier this is with polar integration, which is really the point of this example. So now I can say what this region is with polar variables much easier. Okay, so to do this, now notice that this is the ray, theta equals pi over 6, intersects right here at the point square root of 3, 1. So theta, the outside integral, is going to go from pi over 6 to, this is the ray, pi over 3, right? That's a 60-degree line. And you can see that by playing with the trigonometry of the sides, right? So pi over 6 has a side opposite the sine, right? 1/2, so this is 1, right? With a hypotenuse of 2, right? So that is the y value. So that's why that's 30 degrees or pi over 6. And then a 60-degree angle would have the side opposite is root 3, right? And a hypotenuse of 2. So that's why that is a 60-degree angle or pi over 3. And then the r ranges from, okay, now r goes to, this one's not so easy. R is different for all the different values of theta here. It's not going from a constant to a constant. So what is it going from? Well, it's going from this line, which is y equals 1. But what is y equals 1? That's r sine theta equals 1. Or r equals 1 over sine theta, which is cosecant theta. So it's going from cosecant theta out to r equals 2. And then you can set that up and integrate, and you actually get something pretty simple. So you integrate r, and you get r squared over 2. I'm going to bring the 1/2 out. Evaluate from r equals cosecant theta to r equals 2. Plug in 2, I get 4. Plug in cosecant theta, I get minus cosecant squared theta. Okay, now the integral of cosecant squared is cotangent. I'm sorry, the integral of minus cosecant squared is cotangent. So I get 4 theta plus cotangent of theta from pi over 6 to pi over 3. So I evaluate at pi over 3, minus evaluate at pi over 6, collect all my like terms and simplify, and end up with 1/3 pi minus square root of 3.